back to seating charts, let's think about a more general situation. So in this case, we're going to have N people walk into a cafe, and we want them all to sit down, and they're exactly in chairs. So N people walk into a cafe. So here are my 7 ninjas who enter the cafe. They're going to have different tables of different sizes. So let's give this some notation to that. So we're going to let C1 equal the number of 1 tops, tables that can accommodate 1 person. C2 equal the number of 2 tops. And so on and so forth down to Cn equals the number of n tops. So in this example, I'm going to think of these as 2 tops. So I've got C2 equal to 2. And then I'm going to think of this as a 3 top. C3 equal to 1. There are no 1 tops. And there are no 4 tops. And no 7 tops. So the constraint that I can think about imposing here is that I want to have the right number of seats. So 1 person can fit at a 1 top. 2 people can fit at a 2 top. And so on and so forth. N people all go at the same table if you have an n top. And this has to equal n. So we saw in the previous example that we could count how many ways the people could see this when we had the case of Cn equal 1. So that was the example last time. When Cn equals 1, that means that Ci equals 0 for all I less than n, because we don't have any more room. And we saw that the answer was n minus 1 factorial, but we saw that one way to get it was this guy was the head of the table we thought of, and so it's all ways to arrange them at a bar, putting that guy at the front, and there are n choices for which of those pirates I decided to put at the front. And this is the right way to think about this problem if we want to generalize it. So when we're thinking about it in this particular example with this setup, we want to say to ourselves, well, how are we going to think about sort of dividing out the choices? Well, remember we have a 2 top and a 2 top and a 3 top. And so what we want to do is let's just line up our tables. So we have the 1 tops and the 2 tops and the 3 tops and the 4 tops and so on and so forth. So we put them in that canonical order. As long as you do something canonical, you don't have to think about making a choice. Okay? So we can put them in that canonical order, and now we're going to unwrap them because that's something that we can undo. So how many choices do we have for who we unwrap and put at the head of the table for this one? Well, there are 2 choices because there are 2 people. And the same thing here, there are 2 choices. Here there are 3 choices for who comes first. Okay, but keep in mind that these 2 tops are indistinguishable tables. There's no difference between them. So I need to think about all ways to linearly order the 2 tops. I know that the 3 tops, the bigger tables, come next, but these tables are definitely arbitrarily assigned, so I have to take that into account. So I have 2 factorial ways to arrange them. And now what's the answer that we're coming to? Well, we're going to have to move the pirates out of the way. And what we're coming to is the following theorem, which is the number of ways that we can do this is n factorial, so that's the number of linear orders, bar arrangements, divided by 1 to the C1 factorial. 1 to the C1, you have 1 choice for who's the head of each of those tables, and C1 factorial, put those tables in any order. And now we take the 2 tops, okay? Well, for each 2 top, you have to pick who's first, and then you have to arrange your 2 tops. And keep going, and we get n to the Cn factorial. And this is also, just to make it less cute of a problem, this is the number of permutations of n with cycle type C1 up to Cn. So remember the cycle type, cycle notation for a permutation, if we took a permutation something like 4, 2, 7, 1, 3, 5, 6. So if this is our permutation written in 1-line notation, then we can think of it in cycle type. We say, well, 1 goes to 4. The 4 goes to 1. 2 goes to 2. 3 goes to 7. 7 goes to 6. 6 goes to 5. 5 goes to 3. That closes that, and I believe that that's all of them. So in this example, we would have 1 1 top, 1 2 top, and 1 4 top. So the number of permutations we have with this cycle type would be 7 factorial divided by, there's 1 1 top times C1. So 1 to the 1 times 1. This is our 1 tops. The 2 tops contribute 2 because there's 1 2 top. And then we're just going to get 1 factorial. And then there's a 4 top, which is going to contribute 4 to the 1 times 1 factorial.